It's been a little over a year since the last video on this project. In that period, a number of functional enhancements have been added. So the focus of this video is to demo these new adds. Knowing that everyone's time is limited, I'm not going to go back over things that were reviewed in the earlier videos. However, if this is your first encounter with this project, let me explain the vision behind it. Hams are unique in that they are allowed to build their own gear, specifically their transmitting equipment. Sadly, many in the hobby say, "Yeah, I used to build back in the day," and then offer a litany of explanations as to why it's no longer feasible. Well, to the newcomers, I say it's never been easier. And this project, an HF-CW transceiver, is just one example of what can be accomplished with relatively little cash outlay and using off-the-shelf parts. Now, for those who say, "CW, I haven't got time to learn a foreign language," I hear you. So see my other project, a combination CW decoder and Bluetooth keyboard. Using an ESP32, it can be built for about $30 US, and construction-wise is about as simple as it gets. Or even simpler, use your current computer and software like FLDigi, CW Type, and the list goes on. Bottom line, to find out what's going on in the world of CW, you don't have to spend months, if not years, perfecting that perfect fist and training your ear to convert random dots and dits into words. This simple transceiver can be used by anyone licensed to operate in the HF bands, and I would argue that for QRP work, sending CW with a keyboard is worth one, if not two yes units over the typical manually keyed unit running the same power and antenna. Okay, enough pontification. Let's start by examining the new screen controls and how you might use them. While from a build point of view, having no knobs and switches greatly simplifies the build, operationally, not having them creates a unique set of challenges. A transceiver with a simple, easy-to-use interface goes a long way toward making the radio fun to operate. In its earlier form, the radio's tuning limit was essentially that of the LO frequency, plus or minus 25 kilohertz. For CW work, often that's all that's needed. But most, if not all, the HF bands have CW regions greater than 50 kilohertz. So one way the current firmware expands your ability to navigate up and down the band is via repeated presses of the LO plus and minus buttons. But before we dive into that, notice that when we compare the earlier screen layout to today's version, we see there's now near the screen center an orange button labeled NAR, short for narrow. Let's press it and see what happens. The button label changes from narrow to WID, wide, and the display goes from showing 25 kilohertz of spectrum with the LO frequency at one end to a 50 kilohertz view centered around the LO frequency. This wider view can, in all honesty, be tougher to select a signal. So what I often do is first take a poke at the signal, and if the auto-tune doesn't lock in on it, I'll switch to the narrow view and select the station that way. Once locked to the frequency, it's easy enough to switch back to the wide view. Also notice that as the view is switched, the spectrum boundary frequencies track the change. The earlier version didn't have these indicators. Okay, now let's get back to the LO plus and minus buttons and explore what happens when they're poked repeatedly. Notice in the wide view, each time these buttons are pressed, the blue LO value changes by 25 kilohertz. But in the narrow view, every other press buys you a 40 kilohertz change. This difference in behavior is intentional because at one point this was the only way to move up and down the band. By having two-step increments, it ensured that there would be no frequency blind spots. Clever, but admittedly a kludgy solution. Later updates offer other methods to mitigate this issue. So let's look at another way we can now sidestep this so-called blind spot. Notice that in this wide view, the center of the spectrum is 10135 kilohertz, the LO frequency. What would happen if I wanted to tune to that frequency? Well, it can be done, but if you do, the software ends up trying to demodulate a signal that is zero beat with the mixer oscillator. And an exact zero beat condition would produce a DC output. And honestly, it gets more complicated than that. But bottom line, at this tune point, any power supply noise that might be present gets directly piped through to the speaker. So in an SDR, it's best to have the LO frequency a few kilohertz off of the tune frequency. With this version of the firmware, we can do that by touching the blue LO frequency. With each touch, the LO cycles through three values, the LO plus 10 kilohertz, then the LO minus 10, and then finally back to the original LO value. Which offset to choose will largely depend on what kind of signals are present on the opposite 10 kilohertz image of the selected LO frequency. Often one is just as good as the other, but at times one LO image may have a strong signal at that location, while hopefully the other one does not. So the one without would clearly be the better choice. Up to this point, most features demonstrated have been oriented towards zeroing in on a station that is already on the air. The next tool button I want to showcase is one that might be needed when calling CQ. The situation I'm thinking of is you've called CQ, the returning station can be heard, but it's not on your frequency, meaning the tone of your hearing doesn't match what you selected as the optimum tone. You could use the zero beat button to get his signal to come in where you want it, but that would shift your transmit signal from where it was when you called CQ. The two of you would be on the same frequency, ideal from a bandwidth conservation perspective, but presumably the DX station has opted to reply on a frequency that gives the best incoming tone on his end. You shifting your transmit frequency in response to his reply could lead to the two of you hopscotching up and or down the band. So to sidestep this scenario, you can poke the RIT button, causing the receive side of the SDR to execute the zero beat process, but without changing your original TX frequency. The RIT button is also useful with stations that have a drifting signal. Note, when the RIT function has been activated, you can use the blue and red up-down buttons to apply manual correction to your receive frequency. Finally, you know your SDR is running in RIT mode when you see a green tuning indicator in the spectrum display. And if the difference between the transmit and receive frequencies is sufficient, you'll actually see two tuning markers, red to indicate your transmit frequency and green for the receive frequency. Normal TX equal RX tuning is restored by touching the screen in the spectrum area or by poking the zero beat button between the red and blue up-down buttons. The next new, or I should say changed feature is the FN button, the narrow passband filter. The earlier firmware used an FIR filter with 195 taps. In spite of this large number of taps, the filter, in my opinion, for CW work just didn't perform the way it needed to. And when it came to doing anything else, it consumed so much processing time that it practically put the transceiver to sleep. The internet is rich with proclamations about IR filters requiring less processing power for similar out-of-band signal suppression. But finding how to calculate the needed coefficients proved to be tougher to find. Eventually, I unearthed what I needed, so the original narrowband filter has been replaced with a shiny new IR filter, and given its simplicity, I agree, for narrowband applications, this class of filters does deliver on performance. In my mind, it's essentially a digital Q multiplier. Also, as implemented here, this filter differs from the other two in that its coefficients vary with the side tone selected, meaning it stays centered relative to the side tone frequency you choose. Perfect for CW work, but related to this, there's a bit of a caveat, and I'll explain that later. Anyway, for now, notice the difference in the background noise when the narrowband filter is engaged and when it's not. For me, it really helps to reduce the fatigue that comes with listening to CW on a noisy band. Now, once again, if we compare the earlier display with today's version and look directly below the WWV button, we see a new button labeled CW. I've always touted this rig as a CW rig, but got to thinking, as a receiver, this setup only needs 5 volts, meaning it could be powered directly from the computer's USB port. So, with its 24-bit audio ADC that can listen deep into the noise, wouldn't it make a handy whisper monitor? But being configured for CW, with a side tone set to something like 750 Hz, the receiver is not compliant with the standards used by WSJT, which is calibrated to work with a 2.5 kHz upper sideband filter centered around 1.5 kHz and with an effective side tone offset of 0 Hz. So, to extend the functionality of this receiver, this button, currently reading CW, lets us sequence through 3 demodulation modes: CW, the mode we're in now, upper sideband, and lower sideband, USB and LSB. We'll make use of this later in the video, but let's move on and look at yet another feature. One of the attributes of the HF band is they're not channelized, meaning as long as your signal is within the defined band region, you're free to transmit anywhere you like. Most of the frequency changing techniques demonstrated so far have been oriented toward what I'd classify as search and pounce methods, meaning you see a signal and the firmware has the tools to quickly sync your radio to that signal. But there is also a need just to go to a designated frequency. For example, when the frequency you're on becomes unusable and it's agreed to QSY, say up 5 kHz, or maybe even jump to an arbitrary frequency on another band. With the tuning tools shown so far, this can be a bit of a challenge, if not downright tedious. This firmware, via 2 new hidden buttons, brings some relief to that scenario. These buttons, both at the bottom of the display, one behind the kilohertz group of tuned digits and the second behind the hertz group, provide yet another way to tune the rig. Watch what happens when I poke these 2 areas. The first poke highlights one of the tuned digits with a blue background, and depending on whether the left or right area is poked, the follow-on pokes cause the highlight to index up or down the numbers in the displayed frequency. Now notice the highlight can be moved down to the 1 Hz decimal place, but only up to the 10 kHz decimal digit. Now, as you probably have already guessed, when you see the blue highlight, it means the transceiver is operating in a number-centric tuning mode. To change the value of the highlighted digit, we use the same blue and red up-down buttons used before for tuning changes. A side point to note here is, in this tuning mode, the change is not proportional to the distance from the center, like it is in the other tune modes. Also, technically, you could change the frequency to any value you want using this method, but being limited to 10 kilohertz steps is primarily intended for movement within the selected band. Okay, that pretty much covers the new adds to the main display. There's a minor feature that we can check out by going to the settings screen. Here we'll find a new button labeled TR Timing. Pressing it takes us to this screen. At first blush, it looks more complicated than it is. Here you can change just two settings, the blue TX delay value and the orange TR hang time. These values are for configuring the transceiver's TR relay or switch. What you load in here is dependent on your particular setup. The TX delay should be set to something longer than the time needed for your relay to switch from receive to transmit, and the hang time value is how long you want your radio to stay in transmit mode after a key up condition. The main thing is to make sure the TX delay is set to something longer than what it takes for your switching scheme to connect the antenna to your PA. If it's too short, a mechanical relay closing hot RF will create key clicks, shorten the life of the relay, and maybe even damage your PA. A bad thing any way you look at it. Okay, moving on. Like the other setting screens that have no apparent exit, poke the top status line and the firmware takes you back to the main screen. And final point, if you did make timing changes, don't forget to save them by going back to the settings screen and hitting the Save Settings button. While we're on the settings screen, here's another minor feature that may not be obvious. Poke the screen around its perimeter and notice the red plus sign. Ideally, it should appear right where the screen was touched. This feature is here to help you confirm the Cal touchscreen's accuracy. With so many touch points on the main screen, it's important that we have good correlation between where the stylus touches the screen and where it registers in the processor's mind. It's not likely that the plus sign is going to appear directly under the stylus everywhere it makes contact, but if it's going to be off, I prefer the vertical arrow to be as small as possible. If needed, use the settings screen to go back and repeat the Cal touchscreen process. Often, I can improve the overall results by touching one or more of the calibration points a little off from their shown position. I find it's not about pressing hard, but more about pressing with consistency. Okay, if you're still with me, we're coming down the home stretch of new features. So back on the main screen, the last feature, and I sort of alluded to it when I mentioned using the receiver as a whisper monitor, is the CIV interface has been expanded to operate bidirectionally. The earlier version was limited to reporting the SDR's tune frequency. The current firmware can now respond to incoming commands, allowing software like WSJT to configure the SDR on the fly. Typically, these remote applications have a setup or preference screen that you will need to configure before you can make full use of the application. When you find it, you will usually, via a pick list, like in my example in WSJT, be asked to declare the rig model, pick IC 7300, and then in the serial port configuration, select or set the baud rate to 115200, one stop bit, and no parity. Now obviously this is not a 7300, so don't look for your remote software to magically adjust something like speech compression or any other feature your SDR doesn't have. But it will accept basic commands to change frequency, bandwidth, again limited to your 3 filters, and a few other things like speaker volume and demod mode, our CW upper and lower sideband button mentioned earlier. In my opinion, FL-Rig is a good companion for exploring what can be done via the CIV interface. But since I've been talking about linking it to WSJT, let's continue with that as our remote example and its ability to do band hopping on the bands this rig is provisioned for, 80, 40, 30, and 20 meters. WSPR transmits with a 2-minute duty cycle. Monitoring its progress in real time can be like watching grass grow. So I'm showing this at 16x, with shortcuts back to real time to watch the SDR controlled by WSJT make the band changes. After 10 minutes, here's the website's view of the stations we heard. Note, WSPR transmitters typically run between 5 watts and 200 milliwatts, but some signals can be as little as a few milliwatts. And on this end, the antenna was an inverted V at 25 feet. So, all in all, in my book, pretty amazing. Okay, that's it. Hope you have fun with your next project.